Hi guys, welcome to a lesson of partial differential equations. So in this class, we are going to talk about the method of Cauchy characteristic in higher dimensions. So now previously we discussed the Cauchy characteristic method for two independent variables. And now we will take a problem on three independent variables. So we will see how to solve the problem having three independent variables. So we have a problem that is ux plus x uy minus uz is equals to u. So we can see that we have partial derivatives of three independent variables. So this corresponds that u is a function of x, y, and z. And then we have the initial condition given as xy1 equals x plus y. Now we are going to deal with this problem in the similar manner. First of all, we are going to construct the Lagrange form for this problem. So we have dx over 1 equals dy over x equals dz over -1, and then this is equals to du over u. So we can see that actually we have four differential equations, so four fractions actually. Therefore we can take any of the pairs, but we have to see that which pairs are separable and easily solvable. So if we talk about this pair, this is easy to solve, so it's dx equals dy over x, and this is separable, and when we solve this problem we will get x squared over 2 minus y equals c1. So we can call it equation 1, and then we can take other pair. Say we can take this pair now, this one and this one. So this will be dx over dx equals negative dz, and by integrating we get x plus z equals c2. Now in the previous cases where we have two independent variables, we know that the c2 was actually the function of c1, but for c2 what we need was actually the solution in terms of the dependent variable. Therefore we have to first construct a solution for the dependent variable, which is u in this case. So we can take one more pair with this u to form one solution. So we can take this pair, this is separable, so it will be negative dz equals du over u. Now we can integrate this to get the solution. So it's negative z equals ln u and c3 as well. So c3 minus z equals ln u. Therefore, if we raise both sides on the exponential to get rid of this ln, therefore we will get u equals e to the power c3 dot e to the power negative z. And then we can call this e to the power c3 as a because it's a constant. So we can just make it this way for our e. So we'll get u equals a times e to the power negative z. Now we can call this as equation 3, but the important thing here is that now this a is not only the function of c1, but it's the function of c1 and c2, because now we have three independent variables. So a will be function of two functions, right? So a equals f of c1, which is x squared, this here, over 2 minus y. So we can write x squared over 2 minus y comma c2, that is x plus z here. So we can write x plus z here. Now we can write 3 in this form, that u equals e to the power negative z times function of x squared over 2 minus y comma x plus z. Now the important thing is that we need to apply the initial conditions, but one thing what we can do here to make things easier is that if we assume this function x squared over 2, we can say let v equals x squared over 2 minus y and w equals x plus z. Then we can simply write that this u is a function of v and w. And now it will be easier to apply the conditions, but the initial condition that is given is in terms of x, y, and z. So it's x comma y comma 1 equals x plus y. So in place of this u, we can just plug in x plus y equals e to the power negative 1, because z is 1 here, and then f of v comma w. But here we can see that we have x and y, so we can convert this x and y in terms of w and v from these expressions, these relations. So we can see that simply x is equals to w minus z, and z is 1, so we can write w minus 1. In the initial condition, z is 1, therefore we can write w minus 1. And then for this v, for y, sorry, we can write y equals w minus 1 squared in place of x squared and minus v. And then we can just plug in here these values of x and y. So it will be w minus 1 plus w squared minus 2w plus 1 divided by 2 minus v equals e to the power negative 1 times function of v and w. Now from here, by just simple algebraic manipulation, we can simplify this result. So let's do that. Minus 2v equals or over 2 e to the power negative 1 equals function of v comma w. Then this 2w cancels, and we are left with w squared minus 2v minus 2 minus 2 plus 1 is minus 1 over 2 e to the power negative 1 equals f of v comma w. Now this v comma w is nothing but it's just this function. So again we can write x squared over 2 minus y comma x plus z equals, now we are going to plug in the value of w in terms of x and y from here. So the value of w is x plus z. So we can write x plus z squared minus 2 times v. And v is nothing but x squared over 2 minus y. So it's x squared over 2 minus y. Then minus 1 divided by 2e negative 1. So if we simplify this expression, we will get x squared plus 2xz plus y squared minus x squared plus 2y minus 1 divided by 2e to the negative 1. So this x squared cancels, and we will get e times 2x z plus y squared. Sorry, this is not y squared. Actually, this is z squared. So this is z squared. And here we have z squared. So this is z squared. And then plus 2y minus 1 divided by 2. So the value of this function, that is x squared over 2 minus y comma x plus z, is this whole stuff, right? Now we can just plug in, and we know that this is equals to a, so we can now just plug in this value of a, and we have this expression a e to the power negative z. Therefore, when we apply this a, so we will get the complete solution of this particular differential equation, or we can say the initial value problem. So we have u equals e to the power 1 minus z, and if we multiply these two inside, so we'll get xz plus z squared over 2 plus y negative 1 over 2. And this is the solution to the problem, and we can verify the solution as well. So first of all, we will verify the initial condition, that is x comma y comma 1 equals x plus y. So let's see if we get x plus y or not by plugging this initial condition. So u equals e to the power 1 minus 1 times x times 1 plus 1 over 2 plus y minus half. So this and this cancels out. E to the power negative 1 minus 1, it will be e to the power 0, that is 1, and u is equals to x plus y. So the solution satisfies the initial condition, and let's see whether it also satisfies the given equation or not. So the given equation is ux plus x uy minus uz equals u. So we need to compute these partials. So ux is equals to see the solution. So it's e to the power 1 minus z times z, then uy is equals to e to the power 1 minus z times 1. All right, times 1. Then for uz, we will have negative e to the power 1 minus z times the whole stuff, that is x z plus y plus z squared over 2 minus half. All right, and then plus e to the power 1 minus z times x plus z. Now we need to satisfy this equation, we need to satisfy this equation. So now see here, we can just write z e to the power 1 minus z instead of ux, and then plus x times e to the power 1 minus z instead of x times uy, this thing, and then plus e to the power 1 minus z x z plus y plus z squared over 2 minus half, and minus x e to the power 1 minus z minus z e to the power 1 minus z equals u. So let's see if we get this u or not. We can see that this and this will cancel, this and this will cancel. So we'll get u equals e to the power 1 minus z x z plus y plus z squared over 2 minus half, which is the solution that we already get by solving the problem. So we can see that the result is verified. Therefore, the result is verified, and we are done with this problem. So in higher dimensions, the work is a bit more for these problems that in 2 dimensions, that is sorry, if we are dealing in 3 dimensions, that if we have 2 independent variables, then we only need a function, single function, to find the constant involved in the equation, solution equation. But in this case, when we have more than two independent variables, then we need two functions, right? So that's all for the time being. Hope you guys understand this lesson. Thanks for watching the lesson.